I'd like to thank Henrik for inviting us in to give this talk. This is going to be maybe a little different than some of these seminars. We're going to be splitting up the presentation a bit. So I'm going to talk a bit at the beginning on first of all, the title of this talk is Software-Enabled Cost-Effective Robotics. What really does that mean, and why do we see there being a need for these type of robotic systems? Then I'll back up a little bit and talk some about the company, Energid Technologies. So I'm the CEO of Energid. I'm here with my colleague James English, who's the CTO, and Takeshi Enowaki, who is with Mitsui. And we are basically going to talk about an initiative that we've started recently to develop a software-enabled, cost-effective robotic system with Mitsui. So our belief is that robotics are going the way of a lot of other electronics. They are going to go the way of computers, cell phones, televisions. They're going to get smaller. They're going to be lighter weight. They're going to be much more capable, and they're going to be accessible to more people. Expensive, complex, dangerous robots will give way to simple, safe, affordable robots that can do a lot of useful work. And this is an industry that's been around for a while. There's the industrial robotic systems are pretty impressive. This KUKA robot's got 1,000 kilogram plus payload capacity. It's very fast. It's very good at what it does. But it's used by a small niche of people. Or, it's not something that's broadly applicable. It's difficult, perhaps, to program. Certainly, it satisfies a niche. It builds cars. It does a lot of things. But there's going to be another class of robotic systems. And those are ones that maybe are a lot smaller. Maybe they can only lift 1.5 kilograms for a payload. That's kind of where we see robotics going. To address those types of systems, these what we call consumer-grade robotics, there are going to be advances in both hardware and software. So those types of robots have largely been passed up by the big industrial robotics manufacturers, but is there a market need for those types of robots? And I'd like to propose that there certainly is a market need, because so much of what we do right now of manufacturing is still assembling things by hand. And there's a lot of compelling trends which would say, well, why are we still doing that? For instance, the labor costs are going up. Labor costs in China are going up at a rate of 20% per year. Foxconn, which is a large contract manufacturer, they're actually going to see labor costs go up by $2.9 billion this year alone. So this is changing the equation to some degree. There's also issues with transportation, fuel costs, uncertainty. There's IP issues, something that costs the US estimated about $50 billion per year. So why then is this phone still largely assembled by hand? Why is it done? And it's not that we couldn't, with industrial automation, create work cells that can assemble something like this. The problem really is in the ROI. It's just not cost effective. It's cheaper to get overseas labor to manually assemble things. And there's several reasons for that. If you were going to build an industrial automation or a work cell for doing this, generally it does one thing very well, but it doesn't do a lot of different things. So if you have a lot of tasks, maybe there's hundreds of different assembly tasks for something like this, you need hundreds of different work cells to do that. Procuring the robot is a costly thing for most industrial robotic systems, and the integration cost actually ends up being about 80% of the total cost of automation. So what is that? That's really the software. It's the training. So those things make it so that it's really hard to make the ROI argument for traditional industrial robotic manufacturers. And then what happens? Let's say that you go ahead and you spend all this capital and you do it, and now all of a sudden the iPhone 6 comes out. Well, what do? Now this work cell that you just purchased or just created doesn't really work. It's very difficult for traditional industrial automation to necessarily work with the next generation. What ends up happening is they'll tear down a line and rebuild a line from scratch, which is also a costly proposition. So really addressing these pain points is a very, very big, and we see it kind of as an underserved market. So what is software's role in all of this? How do you enable consumer-grade or low-cost robotic systems? And we believe a large component of that, certainly there's a hardware component, but a large component is a software component. And there's some really compelling trends here as well. If you look at the cost per gigaflop, it's been going down at an exponential rate since the 60s. So since the inception of the first industrial robots, we've actually had exponential reduction in the cost for CPU cycles, which it actually enables us to do things in software that we otherwise couldn't do. If you look at certain, there's like, you guys are probably familiar with some of these low-cost CPUs, like the Raspberry Pi is actually something that you can get for $35, and it's got about a gigaflop. If you look at the specs for the PlayStation 4, you're looking at over a teraflop. If you look at the GPU processing too, and that's about $400. So it's just an amazing cost, basically computational power per cost that you can get. And so compensation through algorithms is really something we can do well today, and it's something that humans do all the time. If I hold up my arm and I'm basically trying to tell you what angle do I have my elbow at? Is it 87 degrees? Is it at 93 degrees? I don't know. I don't really have that sort of accurate encoder information built into my body. Yet by using additional sensory information and by cognition, I can do very complex manipulation tasks that robotic systems can't do. I can use, through visual servoing, I can look at my hand, I can look at what I'm picking up, and I can pick it up. And so these are things that are done and will be done more, we believe, in software. There's additional benefits in that you don't actually have to have inventory with software, and there's no incremental production costs. So that's a little bit of motivation. Now I'll kind of talk some about Energid as a company and how we sort of stumbled upon this, this idea of affordable robotics. And there are other people now working in this area, but we've sort of stumbled upon it ourselves through our own efforts. So the company is headquartered in Cambridge, Massachusetts. We've been around for about 10 years. We have an integration lab in Burlington, Massachusetts, and a small development lab in Bangalore, India. The company has about 20 engineers, so we're a small company, but that's a moving target because we've been growing pretty steadily, and we're growing now. So if anyone's interested in jobs, please come see James or myself after the talk. The company's real core strength is robot software. So we like to say Energid Technology enables complex robotic systems. These are all some systems that we've worked on in the past. Going to the upper left, there's some work that we did for NASA and for JPL. I'll talk a little bit about some of these. But we basically started the company. The company's about 10 years old. Half of that time was really in IP development. We basically were like a technology incubator. Now we continue to do a lot of that core research, government research, but we've actually branched out and we've started to take these advanced algorithms and advanced software and apply it commercially, and that's kind of where the company is going. We started out, our first project was for NASA JSC to develop a velocity control framework for their robots. They were most interested at the time in Robonaut. But they wanted something that would not only work, do very, very fast inverse kinematics, whole body inverse kinematics for something as complex as this, 57 links, 45 degrees of freedom, but it needed to be generic so that it could be applied to all of the robots that they had in their fleet. We then expanded on that software to add a dynamic simulation capability and the ability to, through a turnkey approach, extract a control system and DH parameters from a CAD model, essentially. So we worked with SolidWorks. We created sort of a plugin for SolidWorks that allows you to extract all that the DH parameters, create a control system, but then create a kinematic and dynamic simulation. What the JPL folks wanted to do is they were working on these mobile walking robots. They wanted to be able to make design tweaks, push a button, test it in simulation, see how it worked in real use cases, and then iterate. Concurrent with that, we developed some model-based vision software for the US Missile Defense Agency and the Air Force. And this approach, it's a model-based approach. that essentially can extract 3D information from a single look 2D camera. We actually saw some very interesting stuff that the Georgia Tech folks are doing. You guys are doing. Some of the model-based approaches seem somewhat similar. So out of that, again, this is kind of the first half of the company's history. We developed 2 software products, one we call Actin and one we call Selectin. And Actin is really focused on very enabling complex robotics. It's a software framework. It's a C++ software framework. And Selectin is a very efficient 3D object tracking. One nice thing about the 3D object tracking software is it actually can also track articulation. So you wouldn't just get, let's say you're looking at scissors, you would get position and orientation, but you'd also get articulation. How open or closed are those scissors? So James is going to be talking technically in some detail on these in a bit. So we have applied this a lot of places, applied both our vision and our control software. These are a few of the folks. We've actually segmented Actin into 3 different versions. We have Actin Industrial, Actin Medical, and Actin X, which is a space-based version. Energid's story is kind of how to take, if anyone's familiar with SBIR or for university STTR contracts, which are generally research grants that you can get from the government, Department of Defense, and NASA, and National Science Foundation, and actually commercializing the technology that came out of those. So we've been very successful at being able to do that. And this is just an example of a couple of real-world applications that we're working on today with our machine vision and control software. So we're working on some inspection software for Mitsubishi Heavy Industries. We were working on that. That's actually an older program. We're currently working with Areva on doing something very similar. Areva is a European company that also works in nuclear and clean energy. We're working right now on a project for DARPA. It's called DARPA Phoenix to control arms for a satellite that is a servicing satellite. The idea is that it would service other satellites that have fallen out of a geosynchronous orbit or have some problem that needs to be repaired. We're also working with a Norwegian company that's building they hope for it to be the first autonomous oil drilling rig. It's a robotic drilling rig. And we're using our software for controlling all of the different components of this. That's actually a working live test site in Stavanger, Norway. The actual one that we're working on right now, phase 3, is going to be much, much bigger. And I don't know if this is played or not, but this is a robotic citrus harvesting system. So this is using our machine vision and control to, this is a prototype system that we've been testing out in Florida, in the citrus grove. It has these components that we call them frog tongues that shoot out really quickly. It uses vision to track where the oranges are. Then it shoots these frog tongues out to knock the oranges off the tree. It's actually correcting in real time as it's shooting it out. So it's using like a braking mechanism to steer those. So the actual system will be highly redundant. It's actually going to have hundreds of those sort of frog tongue mechanisms. So through all that, we kind of, and I'll talk a little bit about the history of this, but we've also pursued, through a partnership with Mitsui, a new company that's really focused on software-enabled affordable robotics. And we have a kind of first example of this, and it's a small tabletop robot. We call it the Cyton. It's cost-effective, lightweight, dexterous, easy to task, and inherently safe. And these are all things that we think are important for this next generation of robotic systems. There are other systems, other people are starting to look at this area now, and we think that this is a big opportunity. So the history of how we got involved in this is when we had kind of finished building up that original core IP for Actin and Selectin. We said, okay, well, we have this very complex software. We can control kinematically redundant robots in real time. But we don't have any hardware to show people what it can do. All the hardware that we were working with was NASA, Robonauts, $1 million. There were very limited options for a kinematically redundant arm, especially at the time. We just didn't have the money to go out and buy one. So we decided, why don't we just build a robot arm, a tabletop robot arm that roughly approximates a human arm. 3 degrees of freedom at the wrist, 1 at the elbow, 3 at the shoulder. And That's what we did. The first generation used high-tech servos, actually. And it was just basically model servos. But it was enabled by our software. And it was actually very powerful. And what we saw is we put up a website, a Robai website. We actually had the Robai website much sooner than we had the Robai company. And we started getting contacts from people that were trying to do real work. They were like, we have wanted an arm like this for years, and we couldn't find anything. So we said, hey, maybe we're onto something. And so we started to evolve the design through to the latest generation Cyton Gamma that we have today. And this is still kind of like in the early stages. The Cyton Gamma is still an early stage, and we're looking to take it to the next level in the next year or two. But we actually have over 200 robots out in the wild. Most of them are really for research and education, but there's a lot of these little robots around. And so the features of the robots, they're very easy to train. Basically going back to what we think is going to be important for the next generation of consumer-grade robotics. You can just move the robot where you want it. It will remember it's where you're putting it, and you can actually add. It has a graphical interface that allows you to add pretty sophisticated motions to the general paths. We like to call them cage-free. They're safe to operate around. The kinematic structure. These arms are really lightweight. They're about 5 pounds each. So they're not, they're actually fun to interact with. If you ever saw them, they actually have a little bit of a biological feel to them. They're disruptively portable, we like to call them, because you can actually pick up a couple of them, move to a table, put them down, calibrate, and you're off and running. And that is a big deal for industrial automation, where they might want to have a work cell in one place and then you have to move it. A lot of the times you have to get heavy equipment just to do something like that. And the arms are powerful. They're enabled by the software that we've spent over a decade developing. The arm really has fluid, human-like motion based on our inverse kinematic solution. It kind of has a very biological feel. And there's a lot that you can do with the arm that makes it different than other arms on the market. So we built this, and then as we were doing this, we said, well, we need to compensate for some of the we're using relatively low-cost hardware for this. We're selling the arm for the highest end arm we sell is under $10,000, and that includes all of the software. So we say, okay, well, how do we do that? How are we going to be able to do it? And we have a couple of approaches here. I'll just quickly go over. Basically, we can optimize for heat. The arm can get tired. So let's say you're holding an arm like this for a while, and your arm gets tired. Well, you might want to just move those joints that are overheating. What the software will do will actually reduce the torque on those. But because it's a kinematically redundant arm, you might, for instance, be able to do this and keep the tool at the same position. So you can optimize in ways that allow you to continue to achieve your task while the arm is resting. It also does gravitational torque optimization. I might, if I were picking something up, my wrist isn't that strong, so I might not hold it like this. I might rotate it so that basically the gravity vector is aligned with the axis of my joint. And now I've actually taken basically the torque off of this joint. So the software does the same thing through this, our control solution. We also have ways to do vibration reduction and sag compensation, looking at sensory input. So in the first case, looking at like a 9 DOF sensor, looking at accelerations at the end effector, and in a sort of a fast feedback loop doing some compensations. And sag, basically for sag compensation, using machine vision, using cameras to sort of determine how the arm looks versus how it's expected to look, and closing that loop. But really all of these are enabled by our constraint-based programming approach. So the approach that we take, it's an inverse kinematics type solution that it's very, very flexible. You can specify your constraints and your optimizations on the fly in real time. So with that, I'm going to hand it over to my colleague, James English, and he's going to talk in some details on those frameworks.
Okay, so I'm going to talk a little bit on the algorithms behind the arm. And I'm going to go back. So Neil talked about the Cyton robot. We're applying software to the Cyton that we've used for all those other robots that Neil showed and that we've developed over the years. And what we did with that software, we call it our Acton Toolkit. It's a robot control software. Is we set out to make a generic system that would control any type of robot, any number of joints, any type of joint, sliding or rotating, any number of bifurcations, open and closed chains, things that are open or that come together into a loop. And in particular, focus on control that can meet any type of constraint. So here's some example constraints we wanted to meet. So the traditional one in robotics is positioning and orienting of a tool frame. That's, you get a big industrial arm, it positions and orients something somewhere. But that's just one example of what you might want to do with a robot. I mean, some others are point positioning. You might want to just use a finger to push a button. Or one that's come up surprisingly recently is just orienting. We have work we're doing testing the accelerometers and motion detection in cell phones, where only the orientation changes of interest. How position changes doesn't matter. And some other ones are like pose with a free axis. If you'd imagine if you wanted to place a drill, you might care about everything except how it's oriented around the axis of the drill bit. And distance, you might want to constrain just the joint positions. You might want to add linear constraints to joints. That comes up with industrial arms a lot. Center of mass, if you wanted something to balance, or momentum, if you wanted a robot in space. There's all these different constraints you might want to apply to the robot that go beyond just that pose. And then, in general, the robot, especially the kind of robots we work with, they have more joints than the degrees of constraint that are applied to the system. However those on the previous slide are combined, they don't add up to what the joints add up to. And you'd like with a control system to be able to optimize beneficial things with those extra joints. Right? So some examples, the first two come up all the time. You want to stay away from joint limits and you want to avoid collisions. But other things, like Neil mentioned overheating, you might want to recover from an error. You could also have a locked joint or a free swinging joint. You want to avoid singularities, optimize for strength and accuracy. And also sometimes you just want constraint proximity, like any of those constraints from the earlier slide. Instead of making it an exact constraint, you just might want to come close. So these are some things that you'd want in a generic software for controlling a robot. So you could apply it to any of those types of robots Neil showed earlier. So the approach that we took, which is a good universal approach, is whatever you have, you linearize it. Right? So we take the robot and the constraints that we have, and we linearize it to form the Jacobian equation, which is fairly standard in robotics. The matrix J, all this says is you can find a matrix J that's a function of configuration, that if you multiply it times the joint rates, you get the velocities associated with the constraints. Where those velocities might be linear velocity for a point constraint, linear and angular for a pose, and it's something else for all of those on the list that I showed. And they can all be concatenated together, so you can capture them all in one equation. But what this equation tells you is, given my joint rates, how are my constraints changing? And that's not really what you want to solve with the control problem. It's the flip of that. You say, I want something with my constraints, and I need to solve joint rates, because that's then what I can apply to the robot. So we use this framework to solve. And what it does is it's a generic approach. It lets the user define a set of weights, a matrix W, a vector F, and a scalar alpha, which may be functions of configuration, that then plug into that formula there at the top. Basically, the Jacobian is augmented with a weighting of the null space of the Jacobian, and whatever the constraint velocities are, that's augmented with a weighting of that vector parameter. And that NJ matrix used there satisfies that middle equation. Basically, it's a full rank matrix that spans the null space of the Jacobian. And any spanning set will work there. It doesn't have to be orthogonal or anything, which is helpful in making the algorithm fast. But the bottom line of all this is when you turn the crank on that, you minimize that function there at the bottom, which is a generic quadratic form. And so the behavior you get in the control using this technique comes directly from the meaning behind those parameters, the W, the F, and the alpha. And so, for example, if you look at that equation there at the bottom, if you set alpha to be 0, and W to be the manipulator inertia matrix, it minimizes kinetic energy. If you set W to be some weighting factor and F to be the gradient of a function, you can minimize or maximize that function. So there's lots of different control methods that can be cast into this form. And one thing to add is in addition to that framework, we scale the results. We time scale the results, which helps near singularities, and it helps in other ways give good performance. That's an important factor in the control, actually. It lets you meet joint rate constraints. And then all of this, so all of that was velocity control. We're talking about the rates of the constraints and so forth. What's usually desired by our customers, sometimes it's velocity control, but usually it's position control. I want to position the hand here or a finger here. And so the step to turn that velocity control solution into a position control solution is just simple feedback on the constraint. So like an example is here at the bottom. If you're wanting to place a point, you take the error in that point and you then use that as feedback to calculate the velocity. So those two pieces, that velocity control plus closing the loop around the position using the velocity control, gives a system that solves the position control problem for any robot with one framework. And I have two quick slides here on one other thing that we use in the control, and that's singularity avoidance. So that the total solution method is repeated there at the top. But of course, there's a problem when there's a matrix inverse. So when the determinant of that matrix is 0, that fails. Usually it's failing because the Jacobian itself loses rank, like you're at a workspace boundary or something. It has a physical meaning typically, but the solution method itself fails when that's 0. But this event, actually, people talk about it a lot, but the actual event of that being 0 is very rare. It's a probability 0 event as you're controlling the robot. Instead, practically, what the problem tends to be, it comes up when that determinant changes sign. So from one time step to the next, you started out positive and it's negative the next time step. You crossed a singularity. Somewhere in that time step, all the assumptions you made to form the Jacobian equation went away, right? And so it's a sign of trouble. It may be a workspace boundary or some other very meaningful factor caused that to happen. So what we do with our software is we look one time step ahead and we look for this crossing. And if the crossing occurs, we either stop the arm. That's actually a satisfactory solution more often than you would think. At the workspace boundary, you pretty much just have to stop. Or we can take that constraint and turn it into an optimization, as I mentioned earlier. So here's an example. The robot, this is a simple 12-link mechanism. The robot on the right is stopping at the workspace boundary. You can see that's a point constraint, and it's stopping, while the arm on the left is making it into a soft constraint. So instead of stopping at the workspace boundary, it just traces the closest point. I just was moving the desired placement point with the mouse to generate this. And here's one other example. This is a Motoman robot doing control of all the joints, and simultaneously. And push that optimization factor that's in there, how the kinematic redundancy is used, in this case, is moving the arm away from singularities, which has the extra benefit of optimizing dexterity, if you will, in a way. It optimizes the configuration of the arm for doing tasks. That happens to have, it has two 6-off pose constraints and 15 degrees of freedom. Now, everything I showed so far had fixed base robots, good for industrial applications, but not necessarily good for all types of robots. But it turns out that the framework and the control approach works just as well for mobile robots and for robots where you want to constrain things with respect to other links, not just with the world. So the key part of this is we take one base, what was the base link when it's a fixed base robot, and instead of saying it's fixed, we give it a frame velocity, or a linear plus an angular velocity. And this lets us take do the same math, like this is for a pose constraint. You can write that equation there at the top. It's the old Jacobian equation plus a matrix P times that velocity of the base. So then you can augment that P to the Jacobian and augment the velocity of the base to the Q dot, and you get an equation that has exactly the same form there in the lower left. And because the Jacobian equation has the same form, that same solution method can be used. And so here's an example of a hexapod robot. In this case, it has, all the feet are constrained with point constraints, and I was just with the mouse moving the orientation of the base. So there's no fixed link in this example. And to go back to that slide I showed where we want to be able to meet all those possible constraints, what we have in our software is we have a way to easily add a new constraint. If you have, all you have to do is know how to linearize that constraint and then write it into a strip in the Jacobian. So if you think of a new constraint and you'd like to add it into our software, it only requires writing one new C++ class that just plugs in and everything else works. And one thing of note that we do in our software is if you have a bifurcating robot, a robot that branches like the human body into two arms and then into fingers, you wind up with a lot of zeros in the Jacobian. These joints over here don't have any effect on this end effector. So to really have a well-performing algorithm, you need to manage those zeros. And so we do that. There's a lot of them. We block them off and take advantage of those in calculating that inverse of the augmented Jacobian I showed earlier. So it makes it so that our algorithm runs really fast. Here's just an example on a PC of 35 12-link robots. These are all running, being controlled with 2 end effectors each on one core, actually. So let's see, I have some slides on the 3D vision. We started late. Should I go into it or go? Okay, maybe I'll touch for 5, just quickly go over. Okay, or maybe I should just stop here and Takeshi can go.
Good afternoon, everybody. My name is Takeshi Enowaki, and I'm from a company called Mitsui. And Mitsui is the kind of started out of trading house from Japan. And recently, we own quite a few operating subsidiary, and we try to become kind of conglomerate like other company. Then this is kind of who we are. Our total size asset base is 110 billion. Our sales last year were over 50 billion. We made 3 billion in the profit. So maybe lots of engineers in the room, so I thought number would help us to understand ourselves. And today, I'd like to talk about our robotic initiative with the young company. So actually, I'm from industrial robot division. And we have quite a few subsidiary and project going on. So from next slide, I will quickly go through what we do. And actually, we own the company called Energid Technologies. They are selling the CNC equipment along with Fanuc Robotics. And they are one of the biggest Fanuc robot distributor in the country. And we are selling about probably 250 to 300 industrial robots every year. And we do system integration and turnkey solution providing to the customer. And those companies located in the Council Bluffs, Iowa, which is close to very close to Omaha in Nebraska. And the next project we are doing is we are collaborating with the automotive tier 1 assembler of automotive component. And we support them to develop one specific process of assembly process so that we could license or do something with those technologies in the future. So those 2 areas is existing kind of industrial robot setting we are working with. And outside of the factory, and this is the work we are doing with Kimon in Georgia Tech, and we would like to kind of develop some business in robotic in hospitals and other service area. So this is one of the initiatives we are developing, kind of bioprocessing, automation process in the hospital and other lab. And other hospital initiative is that we made investment, a company called Cyton, which creates some small vehicle within hospital that will be deliver medicine, carotid, stuff like that to other place. And they start break even and they are growing significantly. And the last one is a little bit interesting project, and this is in the entertainment park. The Yasukawa dual-arm robot is creating soft cream and give those things to the kids in the entertainment park. And we do those couple initiatives in Japan, and it starts taking off. And one thing interesting about those business models is usually robot OEM selling robot and making money, but basically we are charging per ice cream basis. So business model on this project is a little bit different from the other things. Then recently, I'm personally very excited, joint venture with Neil and James about Energid. And we really believe those cost-effective human scale arm has lots of future. So we try to set up joint venture, and we are in project. And we are working in 2 phases. First phase is get started, and the second stage is we became company. But in initial joint venture goal of first stage is we will have field beta installation and productize the robot itself, like Neil mentioned. And this is the kind of timeline. And for the first phase, we are supposed to work in 6 months and everything on time, and they are doing excellent job. We are happy, and we are halfway through. So we are discussing kind of next phase. So that's kind of presentation. So thanks so much.
Are there any questions? For any time. So for kinematics and singularities, damping squares often gives pretty good performance. Can you compare what you're doing with the typical damping square?
The question related to damped least squares, which is a technique for working around singularities with robots, and how what we do compares with damped least squares. We have used damped least squares. It's a good technique, and there's, it's a solid technique. Where I would say we essentially do something very similar is when we take the constraint and turn it into an optimization. So that's like, in a way, our approach to handling that. We can work right through singularities with that approach. And the nice thing about that is it lets us optimize a physical thing in the environment. If you say, okay, I want to place this point as close as possible to my destination, you can manage that physical parameter. And if you're using damped least squares, it's more you of course can do optimizations and pick something you want to optimize, but it's more in the velocity control space. So I think they're both good. I just think that's kind of what we use in place of.
You're focused on position control.
Right. Position or position and orientation or another, position type constraint. Yeah, that's a good question. Thank you.
I saw on one of your slides that you had 3 patents on some of this work. Can you comment on what those patents are?
Sure. Well, we have, let me think, we have more than 3, but one patent we have is that the framework configurable, in real time with the scripting language. We also have a patent on using the control system for validating robot designs. So the nice thing there is we actually have a plugin for SolidWorks. So we have a lot of users who would like to make a design in SolidWorks and then start trying to use it and see where it can reach right away. So that's actually a nice tool. We can build a control system automatically and let them do the end effector guidance. And we also, maybe the third one is on the 3D Vision software. I skipped over in the interest of time. Yeah, thanks. Yes?
So you talked about how your system can handle over-actuated links. Can you handle under-actuated links?
Well, I would say there's yes and no. It depends on the level of sophistication in handling the under-actuated links. One thing we certainly can do, and we have it and we do it, is we can pick one link and make it have zero torque. So essentially, it's like it's a free swinging link. You know, we do that from time to time for some purposes. Now that's a little bit different. Maybe you may be thinking, if you had a lot of under-actuated links, how would you plan a path globally from one place to another? I mean, there's lots of questions to answer there that we don't answer, but we do address the local problem of you could just turn off the links, and then how would you move the remaining joints to get a desired motion in the constraints? Does that answer your?
I was thinking more about tendon-driven systems or fingers.
Oh, I see.
Where you have one actuated link that affects multiple systems.
Right, I see. So a good example there, yeah, I see, is like Robonaut hand. So hands commonly, that is under-actuated, yes. And one of the techniques we apply for some under-actuated hands is that we give linear constraints on the joints. I mentioned linear constraints. Sometimes the hands are modeled with linear constraints. If there's something that's not a linear constraint, we could write one new class and plug it in as a special purpose for that hand. But like what we did for Robonaut was linear constraints on the joints. And then what you wind up with then is springs, essentially, that hold those into that constraint in the real system. And then in the dynamic simulation, you'd let those loose and let the spring model of the tendons run. Is that, yeah, thanks. Yeah, that's a good question.
You mentioned that you have to calibrate the robot. You mentioned moving the robot from one table to the other table, and then do some calibration, and then you move on. What do you have to do for calibration?
Well, we need to calibrate the servos, and we need to calibrate the actual location of the arm, depending on as compared to the workspace. Those are the things that come up the most often.
So, like, I guess what's the procedure? Is it time-consuming? Is it a fast process? Have you advanced to that point?
Right. Well, it's probably something that could be improved. It takes longer than we feel like we would like it to. But what we wind up doing right now, we have a program, you can run a program, and then you place the end effector in certain prescribed locations, and you type in where it is. So it's semi-automated. I think there's an opportunity there to make something that's fully automated, and we'd sure like to move in that direction. But it's semi-automated now.
Let's go and thank the speakers again.